So last time I have finished solving the problem on the n particle coupled oscillators, right? So and then I talked about how to find the eigenvalues, eigenfrequencies, and the eigenvectors for this n particles problem. Okay, so and this is the formula for the eigenfrequencies we got, and this is the form of the eigenvectors that we got. So there is just one remark here that I didn't have enough time to finish, is about the possible values of R over here. Right, so when we were in the process of solving this problem, so we call that R can be any integers. Right, so from this slide you can see that. And in principle, right, so from this condition here, we'll conclude that R can be any integers, and that means there are infinitely many choices. However, we do expect that we should only have n normal modes, okay, instead of infinitely many, right? Because we have learned that for two particle system, we have two normal modes, right? So three particle system, we have three normal modes. And now, n particle systems, we expect that there should be just n normal modes. So then the question is, if we put in the numbers R equals n plus 1, n plus 2, what will happen? So that is, if we pick a value that is outside of this range, of the range of 1 to n. So what would we get? So for n plus 1, I think I mentioned it last time, is that if you put R equals n plus 1, right, so to the formula for the eigenfrequencies, well, of course, you will get, again, a number. Okay, so that is actually different from the previous n cases. However, if you try to substitute R equals n plus 1 into the expression of eigenvectors, what you see is that the first element here would be sine n plus 1 pi divided by n plus 1, right? And then, so here, right, so R is n plus 1, here also n plus 1, and so forth. So that means we do have this n plus 1 appears in the numerator, but at the same time, we always have this n plus 1 in the denominator. So that means this n plus 1 factor will just get cancelled. So that is to say, for R equals n plus 1, right, so this sine function will just become sine pi, right? And then the next one is just sine 2 pi. And then the next one is sine 3 pi, and so on. So, and they are all 0, right? So that is, for R equals n plus 1, you just get a 0 vectors as your eigenvectors. Okay. And that won't be a normal mode that we want. Okay. So what about the next one? We try n plus 2. What happened? So R equals n plus 2. Then omega n plus 2 would be this. Okay. And this one can be written as pi divided by 2 plus pi divided by 2n plus 1. Like this. And that would further be equals to this, right? So because sine of x would be equals to sine pi minus x, like this. So then this one, if you again combine all the three terms, then this one you will get n pi divided by 2n plus 1. But what is this? This is exactly equals to omega n. So that is to say, if you substitute r equals n plus 2, then you don't really get a new frequency. Instead, you get just a value that you have seen before already. So how about the eigenvectors? Right. So let me go back to the expression of the eigenvector. So in this column vector, the kth element is written as a sine k r pi divided by n plus 1. Okay. Therefore, for r equals n, right? So the kth element of the eigenvector would be this. So for r equals n plus 2, the kth element of the eigenvector would be, so I'm just skipping the factor of a here. Okay, let me just also write the a over here. Okay. So are these two the same thing? So actually, it can be shown that they are not exactly the same, but they are actually just off by a minus sign. Okay. So to show why is that true, we just need to consider this. Sine this term here plus sine this term here. So we call that the identity that we can use is sine A plus sine B equals 2 sine A plus B times cosine A minus B divided by 2. Okay, so use this identity here. Right, so then the sum of the two sine term would be 2 sine, right? The sum of these two terms divided by 2. Okay, and that you can show that it is just equals to k times 2 times n plus 1 pi divided by n plus 1, which is and cosine something, right? So, but that's not important anymore because this term is actually 2k pi, and therefore the sine of this is 0. So this is 0. Right? So that means, right, so this plus this is 0. That means this is just equals to minus this one. Therefore, the eigenvector for r equals n plus 2 is just the negative of the eigenvector corresponding to r equals n. Right? So that is, we don't really get a new eigenvector. So from here, you can see that if we just taking values, okay, outside the range that we have already selected, we are not getting more eigen frequencies and eigenvectors. So let me just draw a picture here. So I'm plotting omega r versus r. So we call this formula. Okay, so omega r equals 2 square root of k divided by m sine of this. So we plot it as a function of r, right? So you would get a shape like this, right? And then when r equals n plus 1, then we have this value of omega r, but this just gives us a 0 eigenvectors, right? So remember that. So now on the left hand side, right? So we have all the n eigenfrequency located in these positions. Something like that. Right. And once you go beyond n, so this is n plus 1, and then what would be n plus 2? Right. So n plus 2 would be somewhere here. And then this is my omega n plus 2. Right. And you can see that omega n plus 2 is just equals to omega n. If you go further, you'll find that omega n plus 3 is just equals to omega n minus 1, and so on. Okay, in the last slide, Okay, I'm missing a factor of 2 here. Okay, so that is to say this is just k pi, but not 2k pi. Okay, but same conclusion, right? So sine k pi is 0 anyway for all k. Okay, so next, let's look at another n-particle coupled oscillators. Okay, so but with a different geometry, right? So this is a nice example because it basically combines what we have learned about the degeneracy and the n-coupled oscillator. So what we have here, so again, it is an n-particle systems, but this time it's not in this linear configuration. Instead, right? So they are all moving on the same circular hoop, right? So just like the first system in this part of the chapter, right? So at that time we do have 3 masses on a circular hoop. So now we have n. So we are trying to ask the same question, is about finding the eigenfrequencies. And you might still remember that for the case of 3 masses on this circular hoop, we have the so-called degenerate modes. That is, we have more than one mode that has the same eigenfrequency. So here, let's find the eigenfrequencies and show that indeed degeneracy again occurs in this system. So then let's set up the equation of motion. So the equation of motion we have here is basically identical to what we had for the linear n-particle system. Right, so because again, if I just look at the xj, okay, so the jth particle, right, so again, there are 2 neighbors. And therefore, it is experiencing 2 forces by the 2 springs on either side. And because of that, the equation of motion looks like this again. Right, so this form of the equation of motion, exactly the same as what we have here. Okay. So, but what is the fundamental difference between the example we are doing now and this example here? In this example, right, so we said that the 2 ends are fixed. Okay. So, but in this case, with this circular hoop, so we don't really have that fixed point or fixed wall. Okay. So here, let's write down the index more carefully. Okay, so J, so we have x1 all the way to xn, right? So let me just put them down. So we have x1, x2, right? So xj all the way to xn. So here, the j minus 1, right? So when j equals 1, then we will have this 1 minus 1. Then that would be x0, right? So but we don't have x0, right? So let me write down the index more carefully. So let's go from 2 all the way to n minus 1. Okay. For j equals 2, j minus 1 is just 1, that's okay. Right, so on the other hand, right, so if you put j equals n, then this j plus 1 would be n plus 1. Okay. And strictly speaking, we don't have xn plus 1. Okay, but so let me write down the equation of motion for x1 separately then. Just to remind ourselves. So for here, what happened? So if this is x1, so that means that this would be x2, and the one on the left would be actually xn, right? So therefore, what we have is the following. It's minus k xn minus 2x1 plus x2. So one more. Right, so this is for j equals 1. So what about for j equals n? So what is the m d square xn dt square? So in that case, right, so this time if I say that this is xn, right, so then this would be n minus 1, and this would be again 1. So, and therefore this would be this. Okay. So then what are the what's the boundary conditions that we need in this case now? So in the previous example where we have the linear chain, right? So the boundary condition that we were imposing is x0 equals 0, and then xn plus 1 equals 0. So and remember that at that time, this x0 and this xn plus 1 are not really part of the systems, right? So we basically add these two additional masses on the two sides where they are always fixed. So this time, in this case over here, right? So if you are going to define something that called xn plus 1, right? So then what happened is that it must be just talking about x1, right? So that is if I call this, right? So xn plus 1. But physically, right? So this must be just x1. So therefore, this is the conditions that we are going to use, right? This is the thing that actually represent the fact that n masses are put on a circular hoop. So the strategy again would be that we are going to assume that the solution of the displacement take this form. If the couple oscillator is oscillating at a particular normal mode, omega. So first of all, we could just pick phi to be 0, because this is just representing an overall phase shift for all the displacements, for all the oscillate masses. Okay. So, and we are going to require that xn plus 1 equals xn, equals to x1 at all time. So that means sine of n plus 1 gamma has to be equals to sine of gamma. And that means n plus 1 gamma must be close to gamma plus 2r pi. Again, r can be any integer. And that means gamma is 2r pi divided by n. So again, here, r can be any integers. That means we have infinitely many choices. But again, as we have this n particles oscillators, right? So we expect that r just go from 1 all the way up to n, and that's sufficient. So with the gamma here, right? So now we have figured out the sine part of the xj. So the next thing we need to figure out is the omega. Right? So we don't need to do it over again, because remember, how did we find omega in the previous example? In the previous example, after we figure out gamma, we just put this form into the equation of motion. And then we find that gamma square is given by this formula. The equation of motion that we have in this case is the same as the equation of motion that we are considering right now. Right. So therefore, I can still apply the same expression for the eigenfrequency. It's 4k divided by m sine square gamma divided by 2. That right? Yes. So that means omega, right? So it's just 2 square root of k divided by m sine gamma divided by 2. So gamma this time is given here, right? So therefore, we have sine r pi divided by n. So this is the formula for the eigenfrequency omega r. Okay, so we show that. And then one more thing is that I want to investigate the degeneracy of the system. So again, to understand the degeneracy, let me again draw a picture. So omega, first of all, the formula, let me copy the formula one more time. Omega r.